Okay, welcome to the end of chapter 14. This is going to be the end of acids and bases. We just did an example when we're given a Ka and we need to get to pH through something that produces basic solution. But what about when we're going the opposite direction? So this is like a salt whose anion ends up having the neutral properties and not affecting the solution. This will form an acidic solution, and that's because it's a conjugate acid of our weak base. So here's our example, ammonium chloride. When it breaks up in solution, it makes these H plus ions, which will make our solution acidic. Okay, so the reason is that Cl doesn't really have the desire to bond with the hydrogen in water, so it doesn't have an effect. Now here's our example. We have the 0.10 molar ammonium chloride solution, and we're given a Kb with a value here. This is your hint that your reaction needs to produce some NH3. So here's what our reaction will look like. Ammonium and water yields hydrogen ions and NH3. So make your icebox. We know our initial here is 0.10, and we started initially with zeros here. And we can plug in our icebox like normal. But what we need to do is convert our Kb to a Ka, because we're talking about an acid here. Plug it in. Ka times Kb is Kw. And by plugging that in, we end up with our Ka value, and we can plug in what we know to our equilibrium constant here and solve for x. So we solve for x 7.5 times 10 to the negative 6. And that's our H plus. So do we need to convert this? We don't. We can just take the negative log because we're already talking about our H, and we'll get a pH of 5.13. So a little bit acidic, but not very. Okay, so then we have what we call hydrated metal ions. This is essentially when a salt produces acidic solutions because of a metal. So when aluminum chloride's dissolved in water, remember when we saw this back at the beginning of the week, and we talked about how it's hydrated. Well, this extra water on here essentially dissociates to produce an OH and some H plus. We'll notice only one of our waters disassociated. That gave us a +2 charge overall because it used to be +3, and we get these H pluses in solution. Well, what's an H plus in solution going to do? It's going to end up causing a little bit of an acidic solution. So what literally happened was the OH bonds in those water molecules are polarized because of our metal having such a high charge, and +3 is a pretty high charge for a metal. So it makes the hydrogen more acidic. So the higher the charge on a metal, the stronger the acid. So what about if we have a salt where both the ions are reactive? And that's for many salts. They can affect the pH of the solution. Since they'd be pretty complicated, all we need to know really is our outcome. So all we do is compare our Ka with our Kb and say which one's bigger. Whichever's bigger is going to have the larger effect on our solution. So this could be a multiple choice question where they ask you to compare the two. So if Ka is bigger, what's A refer to? An acid, it's going to be acidic. If Kb is bigger and it refers to a base, it's going to be basic, and if they're equal, it's going to be neutral. So that's pretty easy to remember. Okay, sorry, my slideshow just messed up. Alright, here we go. So you could see a question like this. Is NH4F acidic, basic, or neutral? And they'll provide you with this information. Now it's showing my NH3 has a Kb of 1.8 times 10 to the negative 5, and my F minus has a Ka of 7.2 times 10 to the negative 4th. Are these actually what we're talking about in our reaction? They aren't. So we need to just flip-flop them, because technically what produced my NH3 was NH4. So if I turn this into Ka and this into Kb, because my F came from my HF, then I can compare the two. To do that, I'm plugging them into my equation here. I plugged in my Kb down here and my Kw, 1 times 10 to the negative 14th, to get my Ka of NH4. Same thing for my HF. Plug this in for Ka, solve for Kb, and I get this number out. Now I can compare these two. Which one is a bigger number? NH4 because it has a smaller exponent. Well, that's my Ka, that's my acid, so it's going to be acidic. Okay, so now let's think about structure. Because of structure, we're used to thinking that anything with an H out in front might act like an acid, but that doesn't necessarily happen. And there are two things that affect it. First is polarity. We like highly polar compounds, like HCl is an acid. Hydrogen and chlorine are pretty far apart on the periodic table. And we also like a low bond strength because we want them to disassociate. We don't want them to be stuck together. So we don't really want double or triple bonds in an acid. So based on the high polarity of something like hydrofluoric, we might expect hydrofluoric to be strong, but it's actually the weakest. So let's compare these guys. HF, pretty weak because it has a large bond strength. HCl, pretty strong even though these numbers are kind of close. Same with HBr and HI. They're really not far off from each other, so why are all these strong and this one weak? Well, it has to do with the bond energy. This is hard to break. When you get over 500, it's hard to break a bond. So it's hard to break that HF, whereas my HCl is a little bit easier to break. That makes it a stronger acid because it's going to disassociate more easily. So these guys disassociate more easily than this guy does. Now, an oxyacid is something that has an H and then an O bonded to some other item, which is what X stands for. So for any time we're talking about an acid, its strength increases with the number of oxygen atoms that are attached to our central atom. So a bunch of oxygens gives us a stronger acid. Think of H2SO4. Has 4 oxygens attached to it, sulfuric acid. Why does that happen? Because oxygen's really electronegative, and it takes these electrons away from the X and from the OH. So it's really easy to bust this OH off of there in order to create an acid. Here's an example. HOCl is less strong than HClO2, which is less strong than HClO3, which is less strong than HClO4 because of all these oxygens stealing away electrons. Okay, so here are just some examples of how our Ka changes. 3 oxygens over here, 1 over here for a total of 4. Really large Ka value, like 10 to the 7th, that's huge. 3 around it is about 1 for my Ka value. 2, we're starting to get a lot smaller. 1, much smaller. Now let's look at sulfuric. 4 of these guys around them, really large. 3 of these guys around them, getting much smaller. But let's compare. This is on the same level as this guy. What's happening here is my OH is easier to disassociate than my 2 O's were. So this acts almost like somebody that just has 2 O's attached to him because that OH is easy to break off of there. HNO3, very large and has 3 oxygens attached to it because this OH over here can also be easily broken off. Okay, so the whole point is strength is directly related to the number of oxygens. Something else that determines the strength is how electronegative our central atom is. So let's say we have F in the middle. Super electronegative, it's going to have a really strong Ka. But typically, whatever we have in the middle can directly affect our strength. Iodine is a little less electronegative than bromine, which is less electronegative than chlorine, so this one's going to be the strongest down to the weakest. Okay, so how about their properties? When we have an OX bond, it's strong and it's covalent. If X has a really large electronegativity, the bond is obviously covalent, but the OH will be the bond that's easily broken and results in an acidic solution. If they contain a nonmetal, they're considered acidic oxides, and we would show it like this. A nonmetal oxide like SO2 plus water will produce an acid. And when I'm saying that these OH bonds are broken, what I mean is the bond in between here. So I release an H, and that H that's released is what causes it to be acidic. So for example, SO2 plus water is going to become H2SO3 because they're essentially combining to make a bigger compound that's more acidic with these hydrogens out in front. Okay, so what about a basic oxide? This is when something's ionic. And this happens when X has a low electronegativity, because we're talking about a metal here, resulting in some sort of ionic bond that will dissociate in water. These typically make basic solutions, and we call those basic oxides. So here are some examples. If I put this in solution, it would make 3 ions, 2 Ks and an O. This would make a Ca and an O. And what they're going to do is take the OH from that water in order to turn into a base. So we're going to end up with like some sort of Ks dissolved in water, and our H's are going to come join them and leave behind those OH's so that we end up with a basic solution. Now this is the part I said was important at the end. We have to know how to recognize a Lewis acid and base. Remember that Lewis said acids are electron pair acceptors, and what that means is that they are taking some electrons from someone, and a base is an electron pair donor, so they're giving them away. So good diagram here to show us that BF3 ends up taking these two right here and creating a bond with NH3. That makes this guy an acid because he accepted those protons, and this guy a base because he gave them away. And that might be a multiple choice question you'd have to answer, so draw a structure for that. The good thing about the Lewis model is that it kind of covers the Bronsted-Lowry model. And the Bronsted-Lowry model doesn't cover the Lewis model. So the Lewis model is better when we think about things being acceptors and donators. So let's look at these guys. Identify the Lewis acid and base. Well, what is going on here? My NH3 ends up bonding with my Ni. If it has a +2, what does that tell me? That tells me it's an acid, okay? So it's going to accept protons, or rather electrons, accept electrons to try to be neutral. And he's going to lose his electrons. So this guy's going to be the base because he lost them. How about down here? He's positive, so what's he going to do? He's going to accept some electrons and be an acid, and he's going to donate some electrons and be considered a base. And it's exactly how we really thought of it before. So here's a good comparison of our 3 types of definitions that we should know. And here are just some reminders of what to remember. Always figure out the type of solution you're dealing with first. Determine if it's an acid or a base. Then determine if it's strong or weak. And if it's a mixture of acids or bases, determine which one's stronger or has the bigger numbers, so that will dominate your reaction. If you have a salt, determine which ions are reactive and what they're acting like, and use your question to help you with this, because it'll give you hints. Then if you have a strong acid or base, first determine what is contributing the most to your major species, and use that to calculate your pH or pOH by doing the negative log of that. Okay, so what if it's a weak acid or base? First, you're going to determine what controls the pH, so once again, compare it to water, and then write your equation, and it says look up or calculate K. You'll be provided with K. Write down your initial, figure out your change, calculate X, substitute your concentrations back in. Don't forget to do that part just in case it doesn't equal X exactly, and don't forget to do your 5% rule. Then calculate your pH, your pOH, concentrations, whatever the question asked for. So make sure you always go back and check what the question asked for. Alright, I will see you all tomorrow.